This PowerPoint discusses the force of gravity. Gravity is a field force, and what this means is that it is a force that acts over a distance as opposed to acting in contact, like force of friction or normal force. You have to have two surfaces in contact with each other in order for friction or normal force to be applied. If they're not in contact, then those forces don't exist. However, gravity occurs over a distance, so all I have to do is I have to be around Earth in order for its gravitational force to be applied to me. It's called being its gravitational field. So astronauts or satellites in space that are orbiting around, they're actually feeling the gravitational force. The moon is feeling the gravitational force of the Earth as well. Now, the relationship between how far away something is and the gravitational force is referred to as the inverse square law. And what this means is that if you increase the distance between two objects, so let's suppose I got this mass here and this mass here, we got the moon and the Earth. The distance between them, and we have a force that's being applied. Well, if I double the distance, then the force is going to change by the inverse square of the distance. For example, we have twice the distance here. 2 times the distance is the same as 2 over 1, so the inverse is the reciprocal of that. So 2 over 1, the reciprocal is going to be 1 over 2. And then we square it. So 1/2 squared, you take the 1 squared on the numerator, becomes 1. Take the 2 squared in the denominator, becomes 4. So the force is going to be 1/4 because that's the inverse square of 2 times the distance. Now let's look at this example down here. We have 1/2 the distance. With 1/2 the distance, the reciprocal of that's going to be 2, and then 2 squared is 4. So we have 4 times the force. Now the thing that should be intuitive about this is objects that are further apart are going to have less force being applied. And you can see that right here with the numbers. We got twice as much distance means 1/4 the force. Half the distance closer together means you're going to have a greater force. So that's more of a qualitative way of explaining it, that if you increase the distance, you decrease the force. If you decrease the distance, then you increase the force. But the quantitative way to explain that is using the inverse square law, saying that what happens to the force is going to be the inverse square of what happens to the distance. Now the equation, in order to develop the equation, Sir Isaac Newton actually developed the equation, and when he did, he knew a few things about the force. He knew that the force of gravity was affected by two things: the masses of each of the objects and the distance between them. Well, he knew that doubling the distance means that, doubling the mass means that you double the force. So more mass, more force. So he came up with this relationship where force of gravity, and this symbol means proportional. It's proportional to the mass of each object that the force of gravity is between. So if I double the mass, I double the force. I have half the mass, I have half the force. He also knew that the inverse square law applied with the force of gravity. So it was 1 over the distance squared, so the force of gravity is proportional to 1 over the distance squared. Now the reason we use an r is because objects in space, when we talk about gravity, are often orbiting around each other. And when they orbit around each other, so let's say this is my sun, then the Earth, when it goes around, has a distance away that is the radius of the circle. Now you don't take the distance between the two objects and divide by 2 in order to find the radius. The distance that's given is the radius as it's orbiting around. So Sir Isaac Newton took these two relationships and he developed his equation where the force of gravity was going to be equal to mass 1 times mass 2 divided by radius squared. But that wasn't really complete, because over on this side of the equation we got kilograms times kilograms divided by meters squared, but on this side of the equation we have newtons. So we actually have to have something in between that gets the units over here to match up the units over here. And with Kepler's data, him and Newton and Kepler actually worked together, and Newton came up with the equations. Kepler came up with the data in order for Newton to come up with this, which is the gravitational constant, 6.67 times 10 to the negative 11th. That always goes into the equation, 6.67 times 10 to the negative 11th. Then you multiply that by the mass of the two objects that you're trying to figure out the forces between, and the distance between the two squared. Divide by that. Now, if you look at the units, it's pretty weird, but essentially what the units say is we got kilograms times kilograms, so the gravitational constant has to get rid of those, so it divides by kilograms squared. And then we have dividing by meters squared, because that's what the radius is measured in, so the units on the gravitational constant is meters squared, so that cancels top and bottom. But then I need newtons on this side, so then I have newtons there. Essentially, this part right here is not all that important. As long as you have all these numbers in base units, then this will come out into base units also. But it's very very important every single time that you put 6.67 times 10 to the negative 11th into this equation when you solve it. So let's go ahead and use this equation in order to figure out the force of gravity between the sun and the earth. So we have a force of gravity, the mass of the sun is 2.0 times 10 to the 30th kilograms, and the earth is 5.98 times 10 to the 24th kilograms. The average distance between the center of the earth and the center of the sun is 1.50 times 10 to the 11th meters. So what's the force of gravity between the two? We're going to use the gravitational force equation, 6.67 times 10 to the negative 11 times the mass of the earth times the mass of the sun, divided by the distance between the two squared. Now it's very important you remember that squared right there, because that's going to mess up your numbers if you forget it. Punch it into your calculator, you get 3.5 times 10 to the 22nd newtons. So we know we have a force that's acting on the earth from the sun. It's 3.5 times 10 to the 22nd newtons. Well, if we have a force, a net force that's acting on the earth, and we have a mass of the earth, then that means the earth should be accelerating according to Newton's second law. And we know that this is going to be the only force because, well, really there are other forces acting on the earth, but the other forces are so small in comparison to what the sun has that essentially 3.5 times 10 to the 22nd newtons is going to be the only force acting on it. So using Newton's second law, where net force, and the only force we have is a force of gravity, equals mass times acceleration, divide both sides by mass, and we get the 3.5 times 10 to the 22nd newtons divided by 5.98 times 10 to the 24th kilograms. This mass was on the previous slide for the earth. We get 0.00586 meters per second squared. So the question here is, if the earth is accelerating, why isn't it getting closer to the sun? Well, the answer to that is because that even though the acceleration is toward the sun, we're not getting closer. Think about this. On Earth, when an object has a horizontal velocity, it moves horizontally and it curves down towards the Earth. Well, what if the Earth's curvature matches the curve of that object? Let's suppose that object is moving so fast that as it curves, it matches the curve of the Earth. Well, what would happen is it wouldn't actually get closer. It would continue curving around and around the Earth, and even though it has an acceleration, it's just making a loop. Well, the same thing happens between the Earth and the sun. As the Earth is falling toward the sun, it's curving, and it matches the curve of the sun as it circles around. So even though the acceleration is toward the sun, we're not moving toward the sun because velocity and acceleration don't have to be in the same direction. They're actually perpendicular in this circumstance as we move in, not really a perfect circle, but a pretty close approximation of a circle, where the acceleration is toward the center of the solar system, and then the velocity is tangent to that as it moves tangent to the circle as it's going around. So something to notice with this, we have we used this equation in the previous slide to find the acceleration, with the force of gravity divided by the mass of the Earth. Well, we use the force of gravity equation, gravitational constant times mass of the sun times mass of the Earth divided by the distance between the two squared, and then we divide it by the mass of the Earth. Notice the mass of the Earth actually cancels, and we just have the gravitational constant times the mass of the sun divided by the distance between the Earth and the sun squared. Well, something interesting about this is we don't even need to know the mass of the Earth in order to figure out the acceleration. So let's talk about the surface of the Earth. What would the acceleration be at the surface of the Earth? Well, instead of the mass of the sun, we'd use the mass of the Earth because that's where we're accelerating. And instead of the distance from the sun to the Earth squared, we would take the distance from the center of the Earth to the surface of the Earth. So what would the acceleration be? Well, we take the gravitational constant, 6.67 times 10 to the negative 11th, times the mass of the Earth, 5.98 times 10 to the 24th, divided by the radius of the Earth, which is 6.38 times 10 to the 6th squared, and lo and behold, and we get 9.8 meters per second squared. So the reason everything accelerates on Earth at 9.8 meters per second squared is not some magic weird reason. It's because of this equation right here that Newton called the gravitational strength equation. This tells us the gravitational strength of the Earth at the surface, and actually it would tell us the gravitational strength at any point. Technically, if you look at this equation, if we go to the top of a mountain where our radius is a little bit bigger, where we're further from the center of the Earth, then technically the gravitational field strength would be smaller. Our acceleration would be less than 9.8. Now, the amount is so small that it changes only a little bit that you really don't notice that much of a difference, but it would change. So the further you are away from Earth, the acceleration due to gravity actually does change, and this is also called the gravitational field strength. All right, so let's talk about an asteroid that's coming towards Earth. Earth is pulling on a 3.5 times 10 to the 5th kilogram asteroid with a force of 1.72 times 10 to the 6 newtons. How far away is the asteroid from the center of the Earth? Solving for the radius, we would basically switch the radius squared and the force of gravity, and then square root both sides. So rearranging the equation, it would look like this. We go ahead and plug in our numbers, which you get from the problem above. and you see that the radius is going to be 9.0 times 10 to the 6 meters. Now the reason I say this is pretty close is because the radius of the Earth is 6.38 times 10 to the 6 meters. It's 6,400-ish kilometers for the radius of the Earth, and this object is 9,000 kilometers away, which is, well, if you think about the surface of the Earth is 6,400 kilometers closer than the center of the Earth. So really this asteroid's only about 2,600 kilometers away from the surface of the Earth. So let's suppose that you and your significant other are sitting on the couch next to each other, and you, being the sly person that you is, you kind of scoot a little bit closer to your significant other. Your significant other looks over at you and says, "What are you doing?" And then you say, "Well, you know, I learned in physics that if two objects have mass, they have a gravitational attraction toward each other." And then you scoot a little bit closer. Then your significant other looks over at you and says, "Are you calling me fat?" Well, let's actually figure out how much gravitational force would be between the two. So we got mass 1, average male about 85 kilograms, average female about 55 kilograms, and the two are about 1.5 meters apart, which is a good arm's length, arm's width between your hands. So we take the gravitational force equation, we go ahead and plug in our numbers, 6.67 times 10 to the negative 11 times 85 times 55 divided by 1.5 squared, and we get that the force of gravity between you two is going to be 0.000000139 newtons. Well, let's look at this a different way. We have a force of gravity between you attracting you, but what's stopping you from moving together? That would be the force of friction. So let's suppose that we have the surface of your couch is made of the most slick surface we could possibly come up with. There's nothing on Earth that's actually this slick. You don't have two surfaces that can actually have a coefficient of static friction of 0.0001. So let's figure out how much force of friction can be applied, and the upper end of the force of friction is going to be equal to, so the force of friction, the maximum force of friction is equal to the coefficient of static friction times normal force, and since you're dealing with a horizontal couch, then that means the normal force is going to be equal to the force of gravity, which is mass times the acceleration due to gravity on Earth, and plug that in and multiply that out, and you get 0.0833 newtons, which is much, much, much greater than the force of gravity between you two. So obviously you're not going to be sliding because there's no surface that's even that slick in the first place. Alright, so Earth is 81 times more massive than the Moon, but it's only 6 times the amount of gravity. Now before we talked about mass is proportional to force of gravity, so 2 times the mass means 2 times the gravity. So why is it that when Earth is 81 times more massive than the Moon, then at the surface of the Moon the force of gravity is only 6 times greater on the surface of the Earth? So looking at this, the mass is not the only thing that determines how strong the gravitational force is. It's also the distance from the center of the object out to where you're measuring your gravitational strength. So if we look at this, gravity is not only determined by the mass of the objects, but also determined by the distance from the centers of their masses. So why is it that even though Earth is 81 times more massive, that at the surface of the Earth it's only 6 times the amount rather than 81 times? Well, that's because the radius of Earth is also larger. And the larger the radius, the larger you are from the center, gravity goes down. So because of the mass, because it's 81 times more massive, it has 81 times more gravity, but because you're further from the center of Earth at the surface than you are at the center of the Moon from the surface, then you're going to have less gravity because of that, and it balances out to only be 6 times as much. So the Earth has a bigger mass, but it also has a bigger radius. Now it's still, the mass wins over and you still have more gravity on the surface of the Earth than you do on the surface of the Moon, but that's the reason why it's not 81 times more gravity at the surface of the Earth than the surface of the Moon. So how much smaller is the Earth's radius? Well, if you actually calculate it out, the Earth's radius would be 3.67 times the radius of the Moon. And mathematically, that's actually, if you take 81 divided by 6 and then take the square root of that, that's where you get to 3.67. And you can come talk to me about that on how we get that if you'd like. So where does the gravitational constant come from? Well, Sir Isaac Newton came up with a gravitational constant using Kepler's laws, using Kepler's equations and data and all the things that he had. But Cavendish later came up with an experiment in order to determine what the gravitational constant is. Now, if you think about the gravitational force equation, there are several things in there. There's the force of gravity, the mass of each object, the distance between the two. So what Cavendish did is he had this fiber right here. Now, this fiber, what it does is when you rotate an object that's hanging from it, it takes a certain amount of force to get it to rotate, and that's called a torsional force. So this light source hits a mirror that's attached to this cable and then hits a scale. So these two masses right here are not even here yet. Just ignore those right now. And you just have this one bar going across with the two masses that's hanging here, and it's able to hang in equilibrium. So everything's balanced. Now, these two masses are then pulled really close to these two masses here, the smaller masses. Now, because of the gravitational force, these two are going to attract large m and small m. They're going to attract closer to each other, which means that they're going to get closer, which means this fiber cable is going to turn a little bit. Well, I can actually measure the mass of each one of these objects. And because the light source is going to move on the scale because this thing is turning, then I can get the torsional force, which is equal to the force of gravity because they're balancing each other. And then I can physically measure the distance between the two masses. So that's mass 1, mass 2. The force of gravity is equal to the torsional force, which can be found by the angle on the scale. And then I can measure the distance between the two. Well, the only thing in the gravitational equation that you have left is capital G. It's your gravitational strength, or your universal gravitational constant. That's the only thing left in that equation. So that's how he actually came up with that value.